don't know if that was how it was. Either like something when we go through the notes.
Hello, and welcome to another digital design class. In the previous class, we spoke about addition and multiplication of binary numbers. In this class today, we're going to cover binary to octal and binary to hexadecimal. So just give me 1 second to as I mentioned, we went through addition and multiplication. We solved some problems. Today's class, we will focus on converting binary to octal, and also we will continue with how to convert fraction of decimal and octal to a binary number. And if we have time, I would solve some problems, some exercises, some practice problems on how to convert different bases to each other. So for example, the base of 4 to a base of 7, and so on. So as we learned from the previous class, when you want to subtract, I'm just going to go through this very quickly. When you want to add two binary numbers, 1 plus 1 would be equal to 1, 0, and 1 plus 1 plus 1 would be 1, 1. 1, 0 is, as you know, is equal to 2, and 1, 1 is equal to 3. And when we want to subtract, we use the same principles that we have for subtracting two decimal numbers, and we borrow a base when needed. This was an example that we went through. For example, if we want to subtract 0 and 1, 0 minus 1, 0 is less than 1, so we would borrow, and next one would become 1, 0, and we have 2, we subtract 1 of it, and it's left with 1, and so on. Do you want me to solve another subtract, or you're okay with it? I can move on. Move on. Okay. We also learned about binary multiplication. It's the same as decimal multiplication. We multiply one digit in the whole number, and then we write the result, and then for the next digit, we just shift it one digit, and then we add all of them together to get the final results. We also learned about a little bit about number conversion, and the reason that we use octal and the hexadecimal is because it's very easy to convert between octal and binary and octal and hexadecimal, and I'll show you how we do that. Another part that we went through is going from decimal to binary, or for the integer part. We already learned about how we convert binary to decimal. To convert decimal to binary, we just divide that number by the base. Here, the base is 2. So for example, if we want to convert 13 to the base of 2, we divide it by 2. We have the quotient, which isn't important. The remainder is the most important part. We keep that. Then the quotient is divided by 2. We do that until we get a quotient of 0. And we keep the remainders, and we write it in the same order. From bottom to top, we write it as A3, A2, A1, and A0. Or from top to bottom, it's going to be A0, A1, A2, and A3. And we solved a couple of practice problems for this as well. We also learned about converting decimal fraction to binary. To do that, or to any base. To do that, we would multiply that by the base. And we would take the integer, which is 0 or 1, as our coefficient. And we would do that until the fraction becomes 0. We will continue that until the fraction becomes 0. And the coefficients would be our binary number. We solved some practice problems. These are a few other problems. So for example, if we want to convert 175 to the base of 8. I think it's better to go on slideshow. So, and I want you to practice on these as well. Just give me a few seconds. Okay. So we went through decimal fraction. We would multiply them. Now, decimal to octal conversion. If we want to convert decimal to any base, we would simply divide that by that base. I will give you a few minutes to think on this one. 175 and the base of 10, we want to convert it to the base of 8. We didn't solve this last time. No. Okay. Has anyone solved it yet? No. So the first step, we divide 175 by 8. We get 21 quotient, and the remainder is 7. Second step, we divide 21 by 8, and we get 2. And we have 5 remaining, and we keep 5. Again, we divide 2 by 8, and then we get 0. So we will stop here. It's going to be 2. So it's going to be 2 divided by 5. I'm sorry, 2, 5, and 7 is going to be our numbers. So if I convert 257, this is in the base of 10. I want to convert it back to the base of 10. So this is going to be 7 times 8 to the power of 0, 7 times 8 to the power of 1, and 5 times 8 to the power of 1, and 2 times 8 to the power of 2. So this is going to be 7 plus 40 plus 2 times 64 is going to be 128. And when you add them up, you're going to get 175. Another example. We want to convert this to an octal. We have this fraction, decimal. We want to convert it to octal, base of 8. So to convert the base of 10 to the base of 2, and when you had the fraction, you have to multiply it by 2. Here, you have to multiply it by what? By 8, yes, the base. Did anyone solve this one? What is the answer?
0.24. Base 8.
Okay, let's check. So first thing, we have to multiply it by 8. And if we multiply by 8, we're gonna get 2.5. Integer, we keep that as a coefficient. And the fraction is not 0. So we'll continue multiplying the fraction, which is 0.5 by 8. Again, we're gonna get 4. And this time the fraction would be 0. And we keep the fraction, which is 4. So the answer would be 0.24. Now for binary to octal conversion, this table is again very important, and I've already mentioned this. When we have 3 bits in a binary number, the equation is like this. N is the number of bits that we have in a binary number. So if we have n equal to 3, then 2 in the power of 3 is going to be equal to 8. So if I have 3-digit, I'm going to show it with A0, A1, and A2. I can show up to 8 digits. And the digits will be from 0, 0, 0, which is 0, to 1, 1, 1, which is 7. And here I would have 8 digits. So if n is equal to 4, how many digits would I have? 2 in the power of 4 would be, yes, thank you, would be 16. And it starts from 0, 0, 0, 0, goes all the way to 1, 1, 1, 1, which is between 0 and 15, which is 16 digits. And the order is also very important. So 0, 0, 0 is 0, 0, 0, 1 is 1, 0, 1, 0 is 2, 0, 1, 1 is 3, 1, 0, 0 is 4, 1, 0, 1 is 5, 1, 1, 0 is 6, and 1, 1, 1 is 7. Obviously, you can convert this from binary to the base of 10. Let's do this one, for example. This is going to be 2 in the power of 0, 2 in the power of 1, 2 in the power of 2. So 1 times 2 in the power of 2 is 4, plus 1 times 2 in the power of 1, which is 2, equals 6. And the last one is 0. Or this one, you have 2 in the power of 1 and 2 in the power of 0. So it's going to be 2 plus 1 gives us 3. Okay. Is this part clear? Yes. Now, the beauty of an octal system is that we can directly convert a binary to an octal. And how do we do that? If we are given a binary number, like this number over here, we would find the fraction point, and we would simply start from the left. We would divide it into 3-digit numbers. So the first 3 digits I'm going to have is going to be 1, 1, 0. The second one is 1, 0, so I'm missing 1 digit. I can simply throw a 0 on the left side because it's not going to change the number. So I'm going to have another 3-digit over here. So it's going to be 0, 1, 0, and 1, 1, 0. And I do this on the right side as well. Again, I can add another 0 on the right. It's not going to change anything. So I'm going to have 0, 1, 0 here as well. So I've divided into 3-digit numbers, 3-digit binary numbers. So, and then I could look at the table and say, what is 0, 1, 0 equal to in the table? 2. What is 1, 1, 0 equal to? 6. And what is 0, 1, 0 again equal to? So this is going to be 2, 6.2. Just going to erase this because I've already been done. So again, we have 3 digits, 3 digits, 3 digits. We add the zeros, and we would have 26.2. This is not 26, by the way. This is an octal number, okay? If you say 26, you're going to confuse it with a decimal number. This is 26.2 in the base of 8, okay? Because I see sometimes this makes confusion, like 1, 1 is not 11. It's 1, 1. Basically, it's a 3, okay? So, yeah, don't confuse this try to read it this way because it's gonna eliminate any confusion, especially you want to take an FE exam. This is 26.2. Works both ways, binary to octal and octal to binary as well. Now, let's have an example. If we have an octal number, how can we convert it to a binary number? Can you give me an octal number? Anyone give me an octal number with fractions? 72.12. Thank you. 372.12. So the first digit is going to be converted to 3-digit binary. So this is going to be 0, 1, 0. What is 7 equal to in a binary? Thank you. And what is 3 equal to?
0, 1, 1,
Thank you. What is 1 equal to?
0, 0, 1,
And what is 2 equal to again?
0, 1, 0.
So the octal number is going to be 0, 1, 1, 1, 1, 1, 0, 1, 0, 0.001, 0, 1, 0. So now you can see it's much easier to do it this way than to go to decimal and then convert it back and so on. And these are some examples that I saw last semester. So for example, 0, 1, 1, 1, 0, 1, 0.111, 1, 0, 0. We would divide it into group of 3-digit binary numbers. 0, 1, 1 is equal to 3. 1, 0, 1 is equal to 5. So it's going to be 3, 5, and 1, 1, 1 is 7, and 1, and we add 2 zeros. So it's going to be 1, 0, 0, which is 4. Now, what about if I want to do, and I'm going to get back to those examples. What if I want to do a hexadecimal, convert binary to hexadecimal? So for a octal, because we had 3 digits, we would go from 0 to 7. For a hexadecimal, we need 4 digits because we want to show 0 to 15. And 2 in the power of 4, it's 16 digits, and 0 to 15 is actually 16 digits. So we're going to have 16 digits here. And the digits go from 0, 0, 0, 0 to 1, 1, 1, 1. For example, what is 1, 0, 0, 1 equal to? Let's solve 2 of them. And what is 1, 0, 1, 1 equal to? So this is 2 in the power of 0, 2 in the power of 1, 2 in the power of 2, 2 in the power of 3. So it's going to be 8 plus 1. This one is equal to 9. Second one, what is the second one equal to? 2 in the power of 0, 2 in the power of 1, 2 in the power of 2, and 2 in the power of 3. It's going to be 1 times 2 in the power of 3, which is 8, times 0 times 2 in the power of 2, which is 0, times 1 times 2 in the power of 1, times 1 times 2 in the power of 0. So it's going to be 8 plus 2 plus 1, which is equal to 11. In a hexadecimal, we can't show 11. We show it with what? A is 10 and B is 11. So this is equal to B. Okay. And you have it over here, B. I think, yeah, it's this one that I marked with red. Now, if we have a binary number and we want to directly convert it to hexadecimal, this is an example. 10110.01. Again, we start from the fraction point. We put it in the group of 4 digits, but I'm left with 1 digit over here. What should I do? Add 3 zeros here. Same over here, I would add 2 zeros here. Okay. Now, 0, 0, 0, 0, 1, what is this equal to? What is 0, 1, 1, 0 equal to? 6. And what is 0, 1, 0, 0 equal to? 4. Thank you. So it's going to be 16.4. Now, we can do that on the opposite way as well. So we can directly go from a hexadecimal to a binary number. So if someone could give me a hexadecimal number.
742.13.
213. You can make it a little more difficult. Is it okay? I add a few digits. D74213B. Okay. Now I want to convert this to hexadecimal. B is equal to, oh, let's start from this point. 2 is equal to 0, 0, 1, 0. 1 is equal to 0, 0, 0, 1. 3 is equal to 0, 0, 1, 1. And B is equal to 1, 0, 1, 1. And on the left, D is equal to 1, 1, 0, 1. 7 is equal to 0, 1, 1, 1. And 4 is equal to 0, 1, 0, 0. Am I correct? D, thank you, 7, 4, 2, 1, 3, B. I do it in my mind, so please double check it sometimes. Okay. Now I'm going to give you one as a practice. If C point A E. I want you to convert this to a binary I want you to convert this to a binary, and then I want you to convert to a octal number. Has anyone solved it? Has anyone, what is the answer? In octal.
7774.53.
Let's double check it. So F is 1, 1, 1, 1. And suddenly my pen stopped working, so it was FFC.AE. Am I correct?
Yes.
So F is 1, 1, 1, 1. F is again 1, 1, 1, 1. And C is 1, 1, 0, 0. And A is 1, 0, 1, 0. And E is 1, 1, 1, 0. So we start from the fraction point and put in proof of 3. So this is going to be this 3, these 3, these 3, and these 3. And these 3, and we have these 2 left. So 1, 0, 0 is going to be equal to 4. 1, 1, 1, 1 is going to be equal to 7. 1, 1, 1, 1 is going to be equal to 7, and 1, 1, 1 is going to be equal to 7. Did you get the same? So 7, 7, 7, 4. On the other side, 1, 0, 1 is equal to 5. 0, 1, 1 is equal to 3. And 1, 0, 0 is equal to 4. So we're going to have 7774.534. Okay. Is it clear, or do you want me to solve another one?
Makes sense to me.
Since, okay. Can I move to the next one? Next. Okay. These are some problems that I solved for the students last semester. So 267.77. If we want to convert it to octal, 2 is going to be 0, 1, 0, and 6 is going to be 1, 1, 0, and 7 is going to be 1, 1, 1. Again, 7, 7 is 1, 1, 1, and 1, 1, 1. And this is another one, 325.67. We wanted to convert this to binary, this octal number, and then back again to hexadecimal. So when we convert it to binary from octal, it's going to be 3 digit. Every digit is going to be converted to 3 digits. And then we regroup them into 4 digits. And then we convert it back to hexadecimal. And this is another example going from a hexadecimal to binary. B is 1011, A is 1010, and 3 is 011, 0011. And when we want to convert it back, we can convert it back to a octal number. Again, we have to regroup them in a group of 3. And on the other side, the fraction 4 is 0100, C is 1100, and D is 1101. And when we want to convert it back, we would regroup it in the group of 3s, and it's going to be 1653.2315. And this is the one that we solved. This is another example, 6.2. If we want to do the same thing that we got over there, we want to go from octal to hexadecimal. 6 is going to be equal to 110. 2 is going to be equal to 010, and 0.2 is going to be again 010. Again, we could put them in the group of 4s. So we're going to add 2 zeros here and another 0 here. On the right, what is 0100? What is this equal to? 4. What is 0110 equal to? 6. And what is 001? It's going to be 1. So it's going to be 6.4. And hexadecimal. Okay, I'll give you more practice problems in your first homework, which is going to be posted this weekend. Now, this table shows the entire binary decimal and octal hexadecimal equivalence. So decimal 00 is going to be equal to 0000 in binary, and 00 in octal, and 0 in hexadecimal. This goes from 0 to 15 or 0 to F. And you can see from decimal, it's 0 to 15, binary is 0 to 1111. For octal, 1111 is equal to 17. If you want to convert this easily, you can convert it back. 7 times 8 in the power of 0 and 1 times 8 in the power of 1. So it's going to be 8 plus 7, which is 15. 17 is 15. As you can see, for octal, we don't have number 8. Instead, we jump from 0, 5, 7 to 1, 0, which is 8. And then 1, 1, which is 9, 1, 2 is 10, 1, 3 is 11, 1, 4 is 12, 1, 15, 1, 5 is 13, 1, 6 is 14, and 1, 7 is 15. Now, an important part, the next important part is complements. Let me get back to complements. So the way that a computer does subtraction is it does it through actually addition. And it may seem a little complicated at first, but it's a very, I can say, genius way, very smart way to do addition and subtraction using one device. You can do both. And I'll explain to you how we do it. We do it through a process called the complements. We have diminished radix complements and radix complements. This is an example, and we're going to mainly focus in this course on the ones complement. Oh, before I start that, I just want to mention something else. The things that we went through so far, these just work the binary to octal and octal to hexadecimal. You can just do that transmission between binary to octal and octal to hexadecimal. You can't do that, for example, on this number. If I have 4, 5 and a base of 6, and I want to convert it to the base of 12, for example, I cannot do that, okay? For the cases like this, I have to first convert 4, 5 and a base of 6 to the base of 10, and then convert it again from base of 10 to the base of 12, which is going to be a little more complicated, okay? How do I go from 4, 5 in the base of 6 to the base of 10? I will simply divide it by 6. I have the quotient, I have the remainder, I find it in the base of 10 or decimal. Again, I go from base of 10 decimal to the base of, for example, I'm sorry, I did it small. 4, 5 in the base of 6. It's going to be 6 in the power of 0, 6 in the power of 1. I wanted to do it the other way. So this is going to be 5 times 6 plus in the power of 0 plus 4 times 6 in the power of 1. So it's going to be 24 plus 5 gives us 29. So 29 in the base of 10. Now I want to convert this, for example, to the base of 12. I have to divide it by 12. So can you help me on this one? If I divide 29 in the base of 12, what would I have? So it's going to be 2. The remainder would be what? 5. Again, 2 divided by 12. What is it going to be?
Just remainder 2, right?
Yes. So what would the answer be?
2, 5.
2, 5. Let's convert it back. 2, 5 in the base of 12. I want to convert it to the base of 10. This is going to be 5 times 12 in the power of 0, 2 times 12 in the power of 1. Am I correct? So it's going to be 24. 2 times 12 is 24 plus 5 gives us what? 29. 2, 5. Is it clear? So if you want to convert any base to another base, which isn't an octal or hexadecimal, you have to go through the process of dividing it, and it's not going to be as easy as. That's the reason binary and octal hexadecimal, this is the main number systems that we use in our computer system. Okay. This is just a side note for you to know. Yes.
You've had a number like 12.251.
That's a great question. You want to convert it back? You would do exact something.
You had that in decimal. We want to turn it into binary, 0.251 or
So
111, something really
Yeah.
small. That's
mhm.
would be easier to convert it into hexadecimal and then turn that hexadecimal into binary.
No, the binary one is much easier most of the time. But yeah, you can do that as well. But that's a great question. Sometimes it may be easier to go for hexadecimal, but most of the time when I think of the numbers, most times it's easier to do it binary. Binary is one of the easiest ways to base. But sometimes it depends how that number is close to a power of 16, you know. Yeah, but that's a great question. Oh, one thing else that I wanted to mention is let's say, for example, I want to convert 0.6 and the base of 10 to the base of 2. Oh, let's say 0.7. Can you help me with this? What would the result be? So 0.7 times 2 is going to be what? 1.4. 0.4 times 2 is going to be what? 0.8. 0.8 times 2 is going to be equal to what? 1.6. Am I correct? 0.6 times 2 is going to be equal to 1.2. 0.2 times 2 is going to be equal to what? 0.4. 0.4 times 2 is going to be equal to what? 0.8. 0.8 times 2 is going to be equal to what? 1.6. Again, 0.6 times 2 is going to be equal to what? 1.2. So you can see that what happens here is this pattern repeats. So we're going to have something like this. It's going to be start with 1, 0, 1, 1, 0, and then this pattern repeats. Okay. So the 0, 1, 1, because the next one, again, it's going to be 0.4. Again, 0.4 is going to be 0.8, and then 1.6. Again, 1.2. Again, 0.4, and so on. So you can see that this pattern over here, the 0, 1, 1, 0 is just repeating itself. So you have a repeating loop that never ends. Okay. So it's going to be 1, and then 0, 1, 1, 0 is going to be just repeated over and over again. Is it clear? So sometimes that happens. It goes on and on, it's just repeating. Some numbers do that. These are just 2 points that I wanted to mention.
How do you handle that?
Handle back. So again, you want to do it, you just,
Trying to-
it's going to have a little bit of,
It's kind of like if you.
Remainder.
By 3, it's gonna be 0.
Yeah, like, yeah.
Repeating, you
Yeah.
just put that repeating sign over the pattern.
pattern.
It's
10 divided by 3, it's going to be 3.3333. And you want to multiply it, you multiply by 3 again, it's going to give you 9.99999. Like in infinity, it would reach 10. You know what I mean? So, is this clear at this bar? So we need complements, as I mentioned, to be able to subtract numbers in a computer system. And we have different type of complements. We have the first complement, or we call it the diminished radix complement. In a diminished radix complement, by the way, this is for a binary number, all the zeros become 1 and all the ones become 0. In future classes, you will learn about a NOT gate. A NOT gate is basically used in this system. It's going to flip all the ones to zeros and zeros to 1. Okay. Example: 1, 0, 1, 1, 0, 0, 0, 0 becomes 0, 1, 0, 0, 1, 1, 1, 1. So all the zeros become 1 and all the ones become 0. And when you add a number to its first complement, you would have all ones in the system. So 1, 0, 1, 1, 0, 0, 0, 0, plus its first complement, which is 0, 1, 0, 0, 1, 1, 1, 1. It's going to give you 1, 1, 1, 1, 1, 1, 1, 1. Let's solve another problem. For example, I want to find the first complement of 1, 0, 1, 1, 1, 0. What is the first complement for 1, 0, 1, 1, 1, 0? Again, all the zeros become 1 and all the ones become 0. So I'm going to have 1, 0, 1, 0, 0, 0, 1. The first complement is the easiest one. You just flip the numbers, the zeros become 1 and the ones become 0. Is it clear? Okay. The next one is called the radix complement. The radix complement, easiest way that I could ever find the radix is just to find the diminished radix and add 1 to it. So the r's complement or the radix complement of an n-digit number n is in base r is defined as rn minus n, capital N for n not 0, and as 0 for n equal to 0, compared with the r minus 1s or the diminished radix complement, or for example, the binary, the 1's complement, we note that there is the r's complement is obtained by adding 1 to the r minus 1's complement. Since r n minus n is equal to r in power n minus 1 minus n plus 1. Some examples. So for example, for a base of 10, the 10's complement of 0, 1, 2, 3, 9, 8 is equal to 9, 8, 7, 6, 0, 2. And the 10's complement of 2, 4, 6, 7, 0, 0 is 7, 5, 3, 3, 0, 0. Again, for the base of 2, the 2's complement of 1, 1, 0, 1, 1, 0, 0 is 0, 0, 1, 0, 1, 0, 0. And the 2's complement of 0, 1, 1, 0, 1, 1, 1 is 1, 0, 0, 1, 0, 0, 1. Now you may think, how did we get the 10's complement? How did you get this? From this, so 987 from 0, 1, 2, 3, 9, 8. Again, we can go back. For the number 10, if we have a decimal number, base of 10, what are our numbers between? The numbers are between 0 and 9. Am I correct? Yes. So what is the complement of 0? What is the complement of 1? What is the complement of 2? What is the complement of 3? What is the complement of 4? What is the complement of 5? 6, 7, 8, 9, or on that. Okay. Now, I have this number 0, 1, 2, 3, 9, 8. Okay. I want to find the diminished radix complement, meaning the 9's. I'm going to call it the 9's complement. So the 9's complement for this is going to be 1. This is going to be 0. This is going to be 6. This is going to be 7. This is going to be 8. This is going to be 9. So the 9's complement for this. Now, this is called the diminished radix complement. If I want to find the radix complement, I just simply add this number. I add 1 to it. So 987,601 plus 1 is going to give you 987,602, which is the 10's complement. It's called the 10's complete. Let's solve another one.
On your 10's complement, look at 8 on the first one.
It's 987,602. 987,602.
0, 1, 2, 3, 9, 8.
Yes, 0, 1, 2, 3, 1.
Complement of 8 is 1. But our complement number has a 2.
Yes.
There's a similar issue on the second one as well.
Yeah.
I think it should be 753200.
Okay. Okay. And maybe I haven't explained this clearly. The easiest way to find the n's complement is to always find the n minus 1's complement. Okay. This here that I mentioned This is the 9's complement, okay? 9's complement, 0 is 9, and so on. So this one, if I want to find the 9's complement, I just find the complement for 8 is going to be 1. So 0, 1, 2, 3, 9, 8. If I want to find the 9's complement, what would it be? 8 would be 1, 9 would be 0, 3 would be 6, 7 would be 2, 2 would be 7, I'm sorry, 8 and 9. Am I correct? So this is my 9's complement. Now what I would do, I would simply add 1 to it, and I would have my 10's complement. So 9, 8, 7, 6, 0, 2. And here I want the 10's complement, okay? Let me solve a few ones. So I know it's a little confusing. Keep this number in mind, 987602, and write them down. So the number was what? 0, 1, 2, 3, 9, 8. Am I correct? Again, I would find first the 9's complement, and then the 9's complement for this would be 1, this would be 0, this would be 6, 7, 8, and 9. And if I add 1 to it, it's going to give me the 10's complement, which is 2, 0, 6, 7, 8, 9. Okay? And now this is the 10's complement. What happens if I add 0, 1, 2, 3, 9, 8 to its 9's complement? 9, 8, 7, 6, 0, 1. Can you add these two for me together? 1 plus 8 would be what? 9 plus 0 is 9. 3 plus 6 is 9. 9, 9, 9. That's the reason we call it the 9's complement, because you add it, you're going to have all 9's. Okay? Now let's add 0, 1, 2, 3, 9, 8 to 9, 8, 7, 6, 0, 2. 2 plus 8 is what? So I'm going to have a 0. 1 plus 9. 4 plus 6. 1 plus 2 plus 7. 1 plus 1 plus 8. And 1 plus 9. That's the reason we call it the 10's complement. You're going to have all zeros. Okay? Is it clear? Do you want me to solve a couple more? Give me a random decimal number.
2, 3, 7, 6, 4, 2, 1.
And by the way, if I can directly find the 10's complement, but it's going to be a little tricky. So for that one, I have to subtract everything by 10. And doing that is, it's gonna, you have a carry on, it's gonna confuse you. Finding the r minus 1's complement always is the easiest way. So now I want to find the 10's complement for this. What is the 10's complement got to be for this? I'll give you a few minutes to think on it, and then I would solve it. No. I want you to find the 10's complement for this, or the what they call the r's complement, the radix complement for this.
Seven, 6, 2, 3, 5, 7, 9.
Yes, correct. So the first thing that I would do, I would find the 9's complement. So the nines complement, this would be 8, 7, 5, 3, 2, 6, 7. Am I correct? Now, I would simply add 1 to it. So this is going to be 9, 7, 5, 3, 2, 6, 7. So this would be its tens complement. Do you want me to solve another one or? Can you give me a random 4 or 5 digit decimal number?
3.12.
Don't go through fractions yet. I would explain fractions later on, just integer number. Decimal.
No, that,
No, fractions. I'll explain fractions later on. This is just concentrating on. It's gonna be basically the same as well.
0.25 or
No, just integer, just one, like 5,622, something like that.
5,620.
Okay, 5,622. Now give me a 3-digit number. Good, 312. Okay. This is an easy one, but I'm gonna show where do we use complements. Okay. I want you to find the tens complement of 312. Find its tens complement. What is it? 6.
That's
No, the tens is gonna be 8, right?
So 6, 8, 8. The nines complement is going to be, if I want to find the nines complement, it's going to be, this is going to be 7, 8, 6. Yes? And I add 1 to it, so it's going to be 6, 8, 8. Now I want you to add 5, 6, 2, 2 to 6, 8, 8. Eight plus 2 is what? 1 plus 2 plus 8. 1 plus 6 plus 6. 1 plus 5. Okay. We would get rid of the last digit on the left. Now I want to do this. 5622, the original number, minus 312, the original number. What would this give us? $5,622 minus 312. What would the answer would be? Yes. I'm sorry, I did this. You get rid of the last overload digit. So it's going 500, 310. You're going to get the last of the carry on. So you can see that this and this are the same. You get rid of the last carry on when you have a radix complex. Now let's find the ones complement and the twos complement for a binary number, or the radix and the diminished radix for the. Give me a random binary number. Okay. Now I want you to find the twos complement for this. We already learned how to do ones complement. How did we do that? Yes, perfect. So this is gonna be 0, 1, 0, 0, 1, 0. Yes. And we simply add 1 to this. So this is its 1's complement. And now by adding 1 to it, I'm going to have 0, 1, 0, 0, 1, 1. Now this is its 2's complement. This is the 2's. Now let's do a practice problem. Give me a binary number. Someone. 1, 1, 1. Okay. I want you to find the 2's complement for this. I'll give you a few minutes. What is the answer to this?
0, 0, 0, 1, 0, 0, 1.
Perfect. So the 1's complement would be 0, 0, 0, 0, 1, 0, 0, 0. And you add 1 to it, so it's going to be 0, 0, 0, 1, 0, 0, 1. Now let's do another exercise. I want you to subtract 1, 0, 1, 0, 1. And from 0, 1, 0. Do the same exact thing. I would explain about it, how it works, yeah. But use normal, subtraction, borrowing, and so on. Yeah. Yes, that's correct. What is the answer? So 1 minus 0 gives us 1. 0 minus 1, can't do it. We have to borrow from this. And if I borrow from it, what would happen? Do you remember?
2.
I'm sorry? This is 2, it's gonna, or 1, 0, it's gonna be 1. And what about this one? What? Did you get the same one? Let's do it another way. What was the number again? 1, 0? Okay. Let's find the complement of 0, 1, 0. What is the complement of 0, 1, 0? The 2's complement. So the 1's complement for this is 1, 0, 1. The 2's complement is going to be, you add 1 to it. So it's going to be pen isn't working. So 1 plus 1 gives us 0. So it's going to give us 1, 1, 0. Okay. So now what I'm going to do is I'm going to add this to 1, 1, 0. So 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 1 gives us 0, 1. And 1 plus 0 is going to give us 1. And 1 is here. So it's going to give us 1, 0. Sorry, 1, 1, 0, 1, 1. What is 1, 0, 1, 0, 1, 0, 1 equal to? And I'll show you. This is not the final answer. I will show you what we would do. What is 1, 0, 1, 0 equal to? In decimal. This is 1.
What was the question?
2. I want to convert this to decimal. 2 in the power of 0, 1, 2, 3, 4. So this is going to be 16. 2 in the power of 3, 2 in the power of 2. This is 4, 2 in the power of 1, and 2 in the power of 0. Am I correct? 1, 0, 1, 0, 1. 1, 0, 1, 0, 1. In the base of 1, what is it equal to the base of 10? 2 in the power of 0, 2 in the power of 1, 2 in the power of 2, 2 in the power of 3, 2 in the power of 4. 2 in the power of 4 is 16 plus 4 plus 1. 21. What is 0, 1, 0 equal to? What is 0, 1, 0 equal to? What? 2. 0, 1, 0 is equal to 2. 21 minus 2 is equal to what? What is 19 in binary? 16 plus 3, or 16 plus 2 plus 1. 16 is 2 in the power of 4. 2 is 2 in the power of 1. And 1 is 2 in the power of 0. Yes. So it's going to be 16, 1. And then 2 in the power of 3 is 0. 2 in the power of 2 is 0. 2 in the power of 1 is 1. And 2 in the power of 0 is 0, 1. What is the... Can you find any similarities between this and this? What is the difference between this one and that one?
8.
I'm sorry, what?
Difference of the two numbers would be 8. 2 to the power of 3.
It will be 8. I've added them together.
Oh, added. Oh,
Yeah.
okay.
So again, what I have done, the second number, what I did, I found the complement of the 2's complement of that, and the 2's complement of that was 110. Then what I did is I added this to my original number. Let's add it again. Maybe I've done it. 1 plus 0 gives us 1. 1 plus 0 gives us 1. 1 plus 1 gives us 1, 0. And 1 plus 0 is 1. And 1 comes down. Okay. So this is the result that I get when I add them together. Now, what is the difference between this and this? How many digits is there difference between these two numbers? Let's convert this to binary and this one. What is this equal to if I convert it to binary? Decimal. 2 in the power of 0, 2 in the power of 1, 2 in the power of 2, 2 in the power of 3, and 2 in the power of 4. 2 in the power of 0 is 1. 2 in the power of 1 is 2. 2 in the power of 4, 8, and 16. So 16 plus 8 plus 2 plus 1. Am I correct? 16 plus 8 is going to be 24 plus 2 is going to be 26 plus 1 is going to be 27. Why didn't I get the same result that I had in decimal numbers? Why didn't I get the same result in binary? So let's go back to what we did in decimal. In decimal, I found the complement of 10. And by adding the complement of 10 to the original number, original first number, I was able to find the subtract of them. But in binary, I wasn't able to do that. Can someone tell me what happened here and why did I get this result? Think on what happened. So this part is a topic for next week, and I'll explain what happened and why don't we get the results. We have to do some things like, and I'll explain if the second number is greater than the first number, we have to actually find the complement of that number again. That would be our total answer, and I'll explain how all of that is done. And if we have an extra carry on bit, we have to get rid of that. So it's not as easy just adding them. That's not going to work. We have to do an extra step to be able to find the complement and to find the final answer. I don't have enough time to finish this part, but just know for this, just to wrap it up and summarize, we already learned about the first complement. The first complement, you would simply replace the ones with zeros and zeros to one. If you want to find the second complement, what you do is you add 1 to it. So for example, here 1 0 1 1 0 0 0 0 is going to be 0 1 0 0 1 1 1 1, and we add 1 to it. And when we add 1 to it, it's going to be 0 1 0 1 0 0 0 0. And it's the same thing for if we want to find the tens complement, for example, from 9 8 7 6 0 2. First, we find the nines complement, would be 0 1 2 3 9 7. We add 1 to it, and we get 0 1 2 3 9 8. Next class on Thursday, we will learn how to do subtraction by using complements in both binary, decimal, the complement of 2 and complement of 1, and how we do that. And the difference between when we do it with the complement of 1, complement of 2, when we have carry on, when the second number is greater than the first number, when the second number is greater than the first number or less, and when we have a negative answer, and how we determine if this is a negative number or a positive number. Because as you know, 1 0 1, this could be both, and I'll explain how we determine if this binary number is a positive number or a negative number. We have something called a sign bit. This could be, for example, either 5 or it could be +1, for example. And this could be 1 or it could be either -1. Okay, so the first bit is the sign bit, and I'll explain how we determine that in a binary number. When is it positive? When is it negative? That'll usually, we put aside the left number, the first number, as our sign number. If it's 0, it's, for example, positive. If it's 1, it's negative. Some books it's like that. Some books it's the opposite. So that's it for today's class for about complements. Again, we're gonna have some homeworks on this weekend that I would these homeworks would be mainly about base conversion between octal, hexadecimal, binary, and different bases, and also a little bit about complements. Thank you so much, and I'll see you on Thursday.